Okay.
All right. Okay. So we've started the recording. I am Raj Pala. I am part of the Nuclear Engineering Technology program of IIT Kanpur. Welcome to the first talk of 2025. We hope to maintain an active seminar series, all via Zoom, in the hope that we'll have greater large participation in this manner. So we hope to have at least one seminar a month. That's the plan. So it is our honor to have Professor Vijayan as the first seminar speaker of 2025. Currently, he is a professor and dean at IIT-Jammu. Earlier, he has held many distinguished positions at BARC, which I mentioned as part of the seminar announcement. I won't go through that again here. He's been very active in the area of thermal hydraulic design, and this seminar comes at a very opportune moment, given our government's emphasis on increasing the scope of nuclear power production in the country. The government hopes to build on the existing strength and bring in more private partners also. We're hoping that happens soon. Without taking more time, I request Professor Vijayan to share his insights on the role of natural convection in nuclear power production. More are joining. I'll gradually let them in. Um, I request first, maybe we can complete the talk and then take up questions. And the talk will be about 45 minutes and so on. Okay. So, Professor Vijayan, please, you may start.
Thank you. Thank you so much. So as you can see, the title is basically Thermal Hydraulic Design Challenges for Natural Circulation Based Nuclear Power Plants. And if you look at this is my brief outline. So I will not list down each of them. It will I will allow it to appear as we go ahead. So if you look at today's situation, most commercial nuclear power plants, they only switch to natural circulation during pumping power failure. And, if you look at the present day commercial nuclear power plants, the PHWRs, they can generate about 3 to 4% of nominal full flow. And, PWRs, that is about 15 to 20%, whereas BWRs can generate as much as 40% of the nominal flow under natural circulation. And there are several small natural circulation BWRs operating. The Humboldt Bay 3 is the first one, and then that is in US, and Roodward was in Netherlands. And VK50 is the only one that is operating. And all of them, they were of the same, more or less same power, about 65 megawatt electric. And, because of, these small flows, etc., the natural circulation was considered to be a very weak phenomenon. And even several IAEA documents, they mention that, it's a weak phenomenon. But, in 2014, what happened is US NRC certified this ESBWR, which is 1575 megawatt electric. And at that time, that was the highest power reactor to be licensed by a regulatory authority. And this actually changed the perception. Today, nobody talks about natural circulation to be a weak phenomenon. Now, natural circulation, that there are many applications in nuclear power plants, all decay heat removal systems, they are natural circulation. In addition, the steam generators, in PWRs, there are steam generators, which can be as high as 1200 megawatt thermal. And of course, we did talk about ESBWR, it's 1575 megawatt electric. Now, if you look at other fields, in thermal power plant, the largest or highest power thermal power plant based on natural circulation boiler is 60 megawatt electric. And, several of such plants are working in South Africa and Australia. Even in India, many of them are working, but not as high as, see, in India, I think it is about 300 megawatt electric. And these are some of the traditional applications, thermosiphon boiler, reboiler is there in every distillation column. Then there are many others. And innovative applications include, computer CPU cooling, and, many electronic systems are being cooled by natural circulation. And as Professor Rajpala said, one of the emerging applications for natural circulation is small modular reactors, which is, even India is trying to develop now. And then there is this one called infinite mission time passive decay heat removal system. And, even there are several solar nuclear hybrids proposed, the renewables like solar, they can be made a base load power station or 24-hour operating if you actually hybridize with nuclear. And both for solar PV as well as solar thermal, it is proposed. So the motivations is because of natural circulation systems can actually enhance the economics as well as reliability. And the operating and maintenance costs as well as capital costs are less with natural circulation system. And many problems which are found with forced circulation, like flow maldistribution in thermal power plants, this can be easily avoided with the help of natural circulation. And of course, this loss of plant accident like that happened in TMI2 and Fukushima is because of, not from physics point of view, but from thermal hydraulics point of view. And that is because they didn't have what they call the infinite mission time passive decay heat removal. And see, let us look at what are the design considerations for natural circulation reactors. See, the first and foremost is they should have as much high power as possible. The advantage is, if higher the power, the cost per megawatt electric comes down. And if you look at today's commercial nuclear power plant, the only phenomena that limits the power is the CHF. But in case of natural circulation systems, they are also susceptible to instability. So there are two things which can limit the power. One is instability, and the other is CHF. So you can have CHF control design or stability control design in case of natural circulation reactor. And steady state performance is well known. However, stability performance is not that well established. For example, if you look at the literature, it always says, the orificing stabilizes natural circulation system. But then we found that it can also destabilize natural circulation system. We will come to that as we go ahead. Now, coming to the steady state and stability performance of natural circulation systems, as we said, we will show some insights on the steady state performance of single phase, two phase, and supercritical natural circulation systems. And then various instabilities and the stabilizing techniques, again for single phase, two phase, and supercritical systems. And then we also identified techniques which do not reduce the flow. See, orifice, etc. If you use, it will reduce the flow as well as the heat transport capability. Now the question is, what is the best option to stabilize natural circulation system? The question is, can we choose a stabilizing technique without affecting the flow rate and the heat transport capability? Or can we choose a stabilizing technique which can enhance the flow rate as well as heat transport capability? So both are possible. That is what we are going to show. And then this goes on to identify the basic requirements for maximizing the power. Now, knowledge of steady state is important for design, and it is also important for stability analysis. If you use the linear stability analysis, basically we are perturbing the steady state, and you will find the characteristic equation which you derive. There are many, steady state parameters appearing in. So let us look at the steady state. We have developed this equation that is a dimensionless equation for steady state flow in natural circulation system. And this equation is basically developed for cases where fully developed flow prevails. And you can replace the friction factor by a correlation of this type, which is possible for all laminar transition as well as turbulent cases. And here the NG, which is the geometric parameter which is responsible for frictional losses. And you will find if you neglect local losses, it is simply the total circulation length divided by the diameter. However, if you consider the local losses, you will find it is actually L effective by diameter, which is sum of actual physical length plus the equivalent length corresponding to the local loss coefficient, which is calculated this way. And then the GRM which is used here is this one, which is essentially looks like a Grashof number, but then there are differences. And this parameter ISS is actually given by this equation. And this is valid for both uniform diameter and non-uniform diameter loops. Here we are showing that it is actually valid for 3 different loops. There are possibilities. If the laminar flow situation prevails, this is the prediction, and if it is transition or turbulent, it is like this. On the other hand, see, if you look at non-uniform diameter loops, you'll find this is like this. So it's a complex figure of 8 loop, which is basically used in PHWRs. And you find that, the same correlation is not only valid for PHWR, but it is also valid for PWR, VVR, etc., all those loops. And, irrespective of the shape of the loop and irrespective of the fluid, even molten salts and liquid metals also people have tried and they found it is valid. Even in cases, see, natural circulation can be obtained in gravitational acceleration or even with centripetal acceleration, that is rotating thermosiphons, it is called. And as I said, it assumes always, that correlation which we develop, it always assumes that fully developed flow. But if you take a simple rectangular loop with a heater here and a cooler here, and what happens is at the inlet of the heater, the flow is not fully developed. And now you see this is, if you look at the Reynolds number, throughout the loop, it is laminar, right? But then you see what kind of velocity profiles you get in the heater. You get a typical M-shaped velocity profile in the middle of the heater, and which is till the end of the heater, it continues. And once it enters the adiabatic vertical leg, then again the velocity profile development starts, and you get near parabolic profile here. Now, once it enters the elbow, then it gets disturbed, and again developing starts, and you get almost fully developed at the end of the horizontal leg. And again, while entering the cooler, again, it goes through an elbow and again gets disturbed. And in the cooler, you get a W-shaped velocity profile. And as you go ahead, again, it starts developing. You get a flat profile here, and towards the end, it becomes almost parabolic. And again, the disturbance and the development continues in the bottom horizontal line. And this is how it is. There is nothing like fully developed flow profile anywhere. And if you look at, see this portion, if you take, this is the place where the near parabolic velocity profile we found. So you find that still there is significant variation, at least in some parts. And if you take, let's say, an entirely turbulent loop, the story is the same. You find again, say what we call the M-shaped velocity profile. And, when you enter the adiabatic leg, again, it starts developing, but then the flat profile is achieved much faster. And you see that here again, towards the end of the top horizontal leg, you get the flat profile. And in the elbow, again, it gets disturbed. And here, again, the W-shaped profile. And again, it becomes flat profile towards the end. And the story continues, with these disturbances again, and you get this. So again, the situation is there is no fully developed profile throughout the loop anywhere. However, the advantage of turbulent flow is, the developing length requirement is much less. That's why it gives you much better agreement in the velocity profile. Now, if you look at the elbows, what you see, there are recirculations and actually three-dimensional flow profiles exist. And, we also looked at, so the CFD analysis of, nowadays many people see single phase, people say that CFD analysis is robust enough and it can actually give you as good as experimental result. And, here we are finding that, see, you get, comparison with the 1D code, you get about 10 to 13% variation, which is good if your total circulation length is less than 10 meters. But if your total circulation length is of the order of 100 meters, so that's where the nuclear reactors, see, for example, our PSWR, the total circulation length is something around 130 meters. So this is, in this case, we are finding that it is very good agreement. But when you go to, say, a loop which is less than 1 meter, then you find, the disagreement with the correlation is more. And in such cases, you can actually go for loop-specific correlations. Now, if you look at, friction factor data, so, see in the heater, that is where the M-shaped profile is there. And we find, say, it is much different from the parabolic velocity profile, from the laminar and transition and turbulent velocity profiles, what we normally get. So there is some deviation. Whereas if you look at the other places where the parabolic or the turbulent profile exists, there you find, the agreement is very good. Say practically within 1% or 2%, the agreement is good. And that's the reason why the flow predicted is, you get well within 10 to 13% in if you use CFD, and compare with that correlation. So this is that correlation, this red line, blue line, and the green line. They are for laminar, transition, and turbulent region. And, the stars is all CFD prediction. So you get a reasonable prediction with this. Now let's come to stability. If you come to stability, what happens? So you can actually develop a characteristic equation, and a non-dimensional form of the characteristic equation is given here. Over here, this parameter I bar by omega bar, that is basically the theta bar S dz is basically the perturbed temperature distribution over the closed loop, and you have to integrate this. And if you integrate this, you will find a lot of length scales come into this. And you find there are 4 physical parameters: the modified Grashof number, the Reynolds number, the standard number, and the geometric number. And over this, the Reynolds number is a constant, is the steady state value. Now you find that there are a large number of length scales which are needed. So if you go back to the steady state case, all that is required is to maintain just one parameter, that is GRM by NG. If you maintain, the steady state can be simulated in any loop. But stability simulation, you find you have to maintain many length scales. All these length scales are to be seen. That is the hot leg length, the cold leg length, the heater length, the cooler length, and many, and the overall circulation length. All these ratios has to be same. But when we actually did, we made exactly same loop, 3 different loops, and then we actually plotted GRM versus STM. Then we found that they are different, although the length scales are same. But then what we did was, we have RESS given as steady state parameter. It's a steady state equation. So that steady state equation, if we substitute here, then this becomes GRM to the power m and d by lt to the power 1 plus m. And now if you look at, there are only 2 physical parameters, that is the modified Grashof number divided by the ng, and this m is basically is 1 plus, so this, if you take it, m is 1, 1 plus 3 by 3 minus b. As 3 by 3 minus b, it will come, and that value. So only 2 physical parameters. Now, if you keep all the lengths same and plot this parameter for a uniform diameter loop, it becomes d by ng becomes d by lt, and that's why it is. And this becomes 0.5 is to 1.5, and you find in this case, irrespective of the different diameter, you get the same stability map. So that's the advantage of this. The characteristic equation is valid for all the loops, and it is also valid for other shapes. If you want toroidal, rectangular, trapezoidal, all kinds of loops, and you can also use it for nuclear reactors, although the equation will become quite complex. Now, one thing we found that, see, if you look at the effect of LT by D. See, LT by D is, even if you put an orifice, and orifice actually effectively increases the L by D ratio, because you can put the loss coefficient as a function FL E by D. So that's how it is. And now, if you look at the effect of so the LT by D, the lower threshold is varying like this, and the upper threshold is going like this. Now, if you consider, see, this point B, which is unstable, and if you increase L by D, that is, if you add an orifice, what happens? It actually comes into this stable region. However, near the upper threshold, what happens? If you take the point A is stable, but if you add an orifice, you find that it comes in the unstable. So that is the problem. It is not having same effect on the lower and upper threshold. Now, if you look at, see, this is the upper threshold, this is the lower threshold. And the upper threshold minus lower threshold, that is the unstable region. Now you find the unstable region actually decreases with decrease in LT by D. So that means, the lower the LT by D, that it is better. And, so experimentally also we could show this, both the lower threshold and upper threshold. See, usually upper threshold is not visible, if you are doing, actually nobody has done experiments with loop diameters more than 40 mm. And, all the experiments are done in atmospheric pressure, so they could not find the instability. Recently, one of our student, he has done experiments with a 62 mm loop. He wanted to study, whatever people have studied, he doesn't want to study. So he used a 62 mm loop. And then we found that, in his case, he is able to get instability near the upper threshold. And now we will look at what is the
मेरे को तो
efficiency.
मीटिंग दी है ज्वाइन करने के लिए अब ऐसे कोई मीटिंग अटेंड होती है
So I think some disturbance.
Yeah, so can people, others, can they please mute on their side? I'm trying to mute it. Yeah.
Yeah. So let's look at, see, this is one of our students who has tried to find out what is the effect of orifice on the lower threshold. And, see, you find, there are many ways, the threshold can be approached, the operating procedure can be different. And you find that, you start up from rest, you get an unstable, up to 100 watt, it is stable. And if you actually start at a power less than 100 watt, then it is stable. And now you increase the power, then you find that it is becoming unstable only at 240. And now if you also go to an unstable region and reduce the power, then you find that it is a third this thing. So third threshold. So in other words, the threshold of instability actually depends on the operating procedure. And now we use the orifice. So the orifice, without orifice up to 100, it was stable. And, up to 175, it was stable, and 190, it was unstable. And, when you go to this power raising from stable steady state, then it was stable up to 475 watt and unstable at 485. And same here. And if you increase the beta, that means the opening of the orifice is decreasing. That means the loss coefficient is increasing. And in this case, again, it increases. But if you go to a very low value of beta, say 0.51, then we find the entire range is stable. And, actually, what happens is, see, you are not able to get even the lower threshold in this case. Okay, so that is so people get the opinion that this is what everyone has done. Everyone has tried its effect on the lower threshold, and then they found that it is stabilizing. But then, so recently, as I said, Nakul did for the upper threshold, and then we found some surprises. So we are finding, without orifice up to 2000 watt, it was stable. It was a 62 loop. And if you subtract upper threshold minus lower thresholds, actually in this case, the lower threshold, was below the measurement limit, so that's why we are taking it as 0. Even 25 watt was unstable. And that's the same case. Now, when we put orifice is equal to beta with 0.9, again, the lower threshold was very low, and it was not measurable by this instrumentation system. But what we found is 2000 watt was unstable, and that instability continues up to 2500, and 2700 was stable. So which means, the upper threshold minus lower threshold, which is the unstable zone, it increases. If you go to 0.7, at this case, we are finding 100 watt is stable and 200 is unstable. And, here again, 3500 is unstable and 3600 is stable. Again, you find the unstable zone actually increases with orifice. So, but again, when you put beta is equal to 0.5, then an interesting thing happens that, there is no instability till the boiling starts. Even the lower threshold is not reached. So this is the thing. And, so what we found, if you look at, there are many ways to stabilize single phase natural circulation system. Say, for example, if you look at here in this, if you increase the modified standard number, say something more than 4, then there is no instability. And if you reduce the standard number, say over here, the unstable zone keeps on increasing, right? And if you increase the wall thickness, see, this is what we found. If it is 1 mm wall thickness, it's a glass loop. 1 mm wall thickness, it is unstable. But if you increase the thickness to 2.3 mm, then it is stable. Right? And then if you provide, see, the instability was only possible with triplet C loop, that is horizontal heater, horizontal cool. But if you slightly incline the loop, then the instability vanishes. So these are all stabilizing techniques. The insertion of an orifice, also the lower threshold and upper threshold has a different influence, but we will see that. We have already mentioned that actually. Then decreasing the L by D ratio, what happens? So decreasing the L by D ratio has an interesting aspect which we will explain later. Now here, what happens? Increasing the wall thickness or increasing the STM, it does not affect the natural circulation flow rate, and therefore these techniques are preferred ones. But the ideal technique is the one which increases the flow rate and the heat transport capability. And that happens with reducing LT by D ratio. So that is the interesting thing about single phase. And if you go to two-phase natural circulation system, again, two-phase natural circulation system also, if you use the homogeneous equilibrium model, you can get the similar definition or similar studies, exactly similar correlation. The only difference is the geometric number which we calculate, there is a single phase region, there is a two-phase region where the quality changes, and there is a two-phase region where the quality remains constant, especially the adiabatic two-phase pipes above the heater. So there this happens. So all these three has to be accounted. Otherwise, the equation is same. And again, it is based on 1D conservation equations applicable to homogeneous equilibrium model. And that's why we used it, see, even if we use a two-fluid model, people have shown that, the homogeneous equilibrium model is giving good agreement with the two-fluid model as far as natural circulation is concerned. Okay, now moving to, so that this is how that, if you take uniform diameter loops, that is how that correlation performs. It's a reasonably good agreement we are getting. And, this is for non-uniform diameter loops. And again, two-phase non-uniform diameter loops. Again, we are getting reasonably good. Many of these experimental data we have ourselves generated, and there are some which are taken from others. Now, one problem with the two-phase natural circulation system is you will find, if you increase the power, you can get a region where the power, the flow rate increases with power. And you can also have a situation where the flow rate decreases with power. And, in some cases, you get a situation that the flow rate doesn't change with power. And, if you look at, Fukuda and Kobori, they were the first to observe this. And they called this region as, they called originally as gravity dominant region, but, gravity actually is constant throughout. So we call it buoyancy dominant region. So that's the region where the flow rate increases with power. And then there is something called friction dominant region, where the flow rate actually decreases with power. And, we also find there is something called compensating region, where, any increase in the buoyancy force is compensated by a corresponding increase in the frictional force. And that's why, you find that there is no increase in the flow rate. Now, this has some relation to the stability. You will find in two-phase systems, many types of instability people have observed. Static instability, dynamic instability, Dedinek type, flow pattern transition type, and many. But then, I found that Fukuda and Kobori, they have decided, come up with a, only two instabilities, what they call type 1 instability and type 2 instability. Type 1 instability occurs at low quality and type 2 instability occurs at high quality. And, there are so many other instabilities which the literature talks about. They actually fall into either one of these, that is mostly in type 1 instability, especially the acoustic and density wave instability, flashing and geysering instability. All these are covered in type 1 instability. And, if you are doing experiments, you will find, there are, suppose this is initial single phase natural circulation. So that's the loop which we have considered. So this is the kind of loop we took. And in that, we are finding this. There is a low power unstable zone, which he called as type 1 instability. And then there is a high power unstable zone, which is called type 2 instability. Now, this is actually occurring in the buoyancy dominant region. And, it actually is observed right from boiling inception. When the first bubbles start forming, then you get this instability. And whereas type 2 instability is actually occurring in the friction dominant region, where the flow rate actually decreases with increase in power. This is the power increase we are showing. Now, if you look at the type 1 instability, because in nuclear reactors we don't want the type 1 instability. So if we pressurize the system, so this is the case if you are operating it at 1.37 megapascal, that is 13.7 bar. But if you go to 25 bar, we find you get stable single phase flow and stable two phase flow without any type 1 instability. And of course, type 2 instability also, the amplitudes significantly reduce. And, we were designing this ASWR, and, ASWR also have this type 1 and type 2 instability. And a very simple way to eliminate type 1 instability is to have a pressurized startup. And, what we have found, if you have a larger diameter loop, that the instability disappears at a very low pressure. So, for example, this is the experiment which we have done at 5.4 bar in a 19.9 mm uniform diameter loop. The previous one was in a 9.1 mm ID loop. So you can see that beyond 5.4 bar, it is all unstable. Now, if you do a stability analysis, you get a stability map which is more or less looking like the one in the single phase system. But what is happening is inside is stable, single phase, inside was unstable. And here inside is stable basically because if you look at, this is between the two thresholds, it is stable. That is type 1 and type 2. So bottom is type 1 instability and upper one is type 2 instability. Between these two, it is stable. And so actually here we are telling that it is unstable, but the single phase region also occurs here, and you find that single phase region can be stable. Now above the upper threshold, the type 2 instability occurs, and below one, this type 1 instability occurs. Inside it is stable. So this is the typical stability map. Now we are looking at what happens if I change the diameter of the loop or if I change the L by D of the loop. And that effect is shown here. See, if your L by D is, let's say, 871, so that's the highest L by D we found, you find the stable zone is very small. And if you increase the L by D to, let's say, 580, so then you find that much more stable zone is observed. And if you go to, let's say, 435, your L by D is still lower, and it's in all these cases we kept LT same, but the diameter changed, and then we find it is a much more stable zone. And if you continue this way, and if you go to a 40 mm loop, here only up to 20 mm loop. If you go to a 40 mm loop, we find there is no upper threshold. And what it means is, even up to x equal to 1, that is a quality equal to 1, you find type 2 threshold is not observed. In other words, type 2 instability disappears if your diameter is more than a particular value. So if you look at the stabilization techniques for two-phase natural circulation, one of them is, this is subcooling. Subcooling is inlet subcooling they talk about. That is, the entry to the heater is normally a subcooled liquid. And, it is Tsat minus T, that is inlet subcooling. And, you find as inlet subcooling becomes very large, say, in this case, say maybe something around 13 or 14, then we find everything is unstable. However, if you decrease the inlet subcooling, then you find that the stable zone is increasing. And another thing is, if you increase the pressure, again, you'll find it's stabilizing. If you decrease the LT by D ratio, that is what we are going to show. So if you decrease the LT by D ratio, again, that's what we have shown here. If you decrease the LT by D ratio, then the stable zone is increasing. And insertion of one orifice actually increases the LT by D. And therefore, actually, if you look at the literature, LT by D, if you insert an orifice, it stabilizes. But it actually only stabilizes the pump circulation loops. Pump circulation loops, you can actually select a pump of a higher developed head, and in that case, the single phase pressure drop can be dominant, and that way it can be avoided. But in natural circulation systems, it cannot be avoided by inserting an orifice. And the wall thickness also, can be little effect on stabilize, because in two-phase natural circulation where once boiling sets in, then there is no change in the loop temperature, and therefore there is no change in the wall temperature. There can be slight effect, but not that. But what is important is decreasing the LT by D ratio actually increases the flow rate as well as the heat transport capability, and it also stabilizes. That is an interesting thing. And then the problem is, this is the challenge. Once you have already designed the loop or the reactor, you now cannot change LT by D. But during the design stage, you can change, and subsequently you cannot change. Whereas in a pump system, if you find that it is, the pump, it is unstable, then you can just change the pump, and this has been done in many reactors. So they change the pump, then you can get a stable system. But that option is not available. However, you can increase the inlet subcooling, or you can increase the pressure, but insertion of an orifice is not going to help. That's the. And then if you look at what limits the maximum power in two-phase natural circulation system, we talk about in boiling or pump systems, it is only the CHF. But you will find in a two-phase natural circulation system, this is your type 2 threshold, this is your type 1 threshold. Outside it is all unstable, and your CHF threshold is much above the stability threshold. So that means it is in the unstable zone. So this system, if you want to design it, is stability control. But you can also have a situation, half of it is CHF controlled, where this part is CHF control and this part is stability control. And if your CHF threshold is well inside the stable zone, then you can say that it is stability control. Then it becomes like our boiling water reactors with pump, where it is CHF control. And what happens? What about supercritical natural circulation system? Now, if you have a single phase natural circulation system, and as you keep on increasing the pressure, and when you go through the pseudocritical region, then you find there is a steep change in fluid properties that is happening. A steep change in density is happening. Okay, I have a lecture I'll call you. So when the single phase system goes through this pseudocritical region, then you encounter instability. And of course, there is a dimensionless correlation. See, when you have this kind of variation, it is very difficult to use that Bosniak approximation which people use for natural circulation. So you have to use something else. For example, this Ambrosini and Sharabi, it's two recent papers. They showed that if you plot rho star versus H star, rho star is rho by rho PC. That means density divided by density at the pseudocritical point. And here again, this PC stands for pseudocritical point. And if you plot in this fashion, then they found that for all the fluids, it actually goes through a unified curve. It's all becomes a single curve. And however, the steady state, you can get more or less the same correlation that we are using in single phase natural circulation. Here again, we did experiment and we checked the validity of the steady state correlation. And we did experiments only with carbon dioxide and water. And in both cases, there is plus minus 20% within that you get, especially the one which is in the pseudocritical region. Away from the pseudocritical region, you can use the single phase. So you are getting a much better agreement, with the literature data, and they are much better agreement. And we have done this loop, with both carbon dioxide and water. Now, if you look at the stability, so this is the stability map typically which you will get. And the stability map is much similar to the single phase case, and in which case, we found between the lower and upper threshold, it is unstable. So in single phase and two phase, between the lower and upper threshold, it is unstable. But then, what is the effect of L by D? L by D has a mixed effect in supercritical system. For example, if you keep on increasing your L by D ratio, that is, if you go to a smaller diameter loop, so this is a 14 mm loop, what you find is your unstable region becomes very narrow. And other thing is, so unstable region becomes very narrow, that means, you are stabilizing. But, if you look at the heater inlet temperature, you find that the instability persists, up to about, say, 365, whereas, the 374 is the critical temperature. And, if you look at, say, L by D of, say, this was L by D 1000 for 14 mm. If you go to 20.7, now you find, the unstable region has shifted up. So, in addition, the unstable region has increased. But then, what happens, it is, see, this shifting up is, is stabilizing. And, you find that it is disappearing at a lower temperature, which is also stabilizing. But, widening of the unstable region, that is destabilizing. That's why we say that it is mixed effect. So in this particular case, you can have an orifice and you can stabilize this loop without any problem. And we found especially in small diameter loops, the unstable region is a very narrow one, and it is around the pseudocritical. So the red line is the pseudocritical line, and the uh, dotted line is the critical line. So you find that it is a very narrow region in which the instability is obtained. And actually, while we were doing experiment, initially we were using large power steps, and when we were using large power steps, we were never getting the instability, and we thought the system is fully stable. But then when when we reduced the power step to as low as 250 watt, then we found that there is a narrow region which we were escaping when we were using a large step in power. So here again, it is showing this instability, and you get a reasonable agreement. Even if we use supercritical water, then also it is the same situation, and this is the predicted stability is in reasonable agreement with the data. Now, again, stabilization techniques for supercritical natural circulation. So we find that increasing the secondary coolant flow rate, that is actually that is what it is showing. If you increase the secondary coolant flow rate, what happens? Your stability zone or unstable zone goes to higher and higher powers. So that's why. And then if you increase the pressure here, see, for example, if you go beyond, let's say, 23.7 or so, see, you find there is no instability. That is 23.7 megapascal, that is 237. Okay. So pressure, increasing the pressure is stabilizing. Increasing the heater inlet temperature is again, if you increase the heater inlet temperature, you find that beyond a certain critical value, it is not found. Instability is not found. And then increasing the wall thickness, this also we found in supercritical loop, it becomes stable if you increase the wall thickness. Then L by D has a mixed effect, we already said. In some, it actually shifts up. If you look at this, it shifts up the lower and upper threshold. In that sense, it is stabilizing, but it widens the unstable zone, and in that sense, it is destabilizing. And then, if you look at the L by D ratio, decrease in unstable zone, decreases the unstable zone and hence is stabilizing. It's L by D ratio. But then, if you will find, see what is happening is, if you lower the L by D ratio, you are coming to lower and lower pressure. The unstable zone comes to lower and lower power. So higher power, it is always stable. So in that sense, it is stabilizing. But L by D ratio also widens this unstable zone. In that sense, it is destabilizing. So that's what it has got two effects, so mixed effect. And in this case, also, the orifice can stabilize or destabilize as in single phase natural circulation. And the techniques that increase the heat transport capability while stabilizing are reducing the L by D ratio and increasing the secondary coolant flow rate also does that. And increasing the pressure and wall thickness does not affect the heat transport capability, but it actually stabilizes them. Now, just a few discussions, see, we found in case of, so kind of a summarizing, in case of single phase loop, we found insertion of an orifice actually stabilizes the lower threshold, but it destabilizes the upper threshold. And in case of two-phase natural circulation, it is always destabilizing. And in case of supercritical natural circulation, there is a mixed effect. And techniques that increase the heat transport capability while stabilizing. For example, reduction of LT by D, it stabilizes single-phase natural circulation as well as two-phase natural circulation. But you have a mixed effect for supercritical natural circulation. and then increasing the pressure. Say single phase loop practically has no effect. But then in case of supercritical and two-phase natural circulation, you find increase in the pressure stabilizes. And techniques that does not affect the heat transport capability while stabilizing. So increasing STM or secondary flow rate, that is modified standard number, does not affect the heat transport capability, but it stabilizes. While increasing the inlet temperature in two-phase natural circulation and supercritical natural circulation also is stabilizing, and increasing the wall thickness is also stabilizing. Okay. Now, if you look at supposing if you have to design a natural circulation reactor, what is the best way? See, if you look at, nowadays, there are many natural circulation-based nuclear reactors being developed, and many of them are single-phase natural circulation, especially the SMRs. Many SMRs are being developed under single-phase natural circulation. And two-phase natural circulation, you can have high power, because in two-phase, you have much larger driving force compared to single-phase. So natural circulation reactor design with supercritical natural circulation is good. You can have high power, but you cannot have outlet temperature more than 430 degrees centigrade. So beyond this, what we find its effect is not. The natural circulation flow is not increasing much. That's the reason. And two-phase and supercritical natural circulation-based reactors are more economic than single-phase natural circulation reactors. Basically because two-phase and supercritical systems do not need a steam generator, whereas single-phase system, they need a steam generator, and that's why it is more economic. And then, maximum heat transport capability, if you look at natural circulation reactors, you can go for low LT by D ratio to enhance the flow rate and heat transport capability, and also to stabilize the system. And, see low core height, core is the one, core and steam generator is the one where you have the smaller hydraulic diameter. And, if you have smaller height, then you will find that it can actually, in the core as well as in the steam generator, then you will find that it will reduce the LT by D ratio and therefore increase the flow rate, and that will increase your heat transport capability. And you will find vessel type design much better than the pressure tube type design. So this is something which people have seen. Say, for example, you would have seen in one of the initial slide, I said PHWR, say can give only 3 to 4%, basically because the LT by D ratio in one pass of the PHWR is 1000, and two passes it is 2000, and both the steam generators put together it is another 1000. So it's a very high LT by D ratio, and that increases the frictional pressure loss. Whereas if you go to two-phase natural circulation, you find that the vessel type design is much better. And, see natural circulation ESBWR, it is a vessel type design. You can go for 1575 megawatt electric. Whereas as we talked about natural circulation boiling water, boilers, which are in the thermal power plants, and 660 megawatt electric is operating, but they are all pressure tube type. So that's the reason they are not able to go to this level. Now, what is needed is, you need to have high surface area density. Now, if you use the solid fuel rods, you are not going to get high surface area density. One of the option is to use annular fuel. Annular fuel, which means the inside and outside cooled annular fuel, and this has been studied a consortium of Koreans and Chinese as well as Americans. They studied because this can give you much larger power. Because what happens is the heat transfer area increases, and therefore the CHF, significant enhancement in critical heat flux, can occur if you use this, and that's why it increases the power. And if you use plate type fuel, we only use in nuclear research reactors. But a plate type fuel, if you can use in, let's say, in case of power reactors, you can have very, very high surface area density, and therefore the CHF can be much more enhanced. And this we already said, buoyancy driving force in single phase natural circulation is less compared to two phase and supercritical natural circulation. So that's the reason why supercritical they are. However, if you go to this kind of high surface area density, I feel today people are talking about 300 megawatt electric. They are talking about natural circulation single phase reactor, but you can go up to 600 megawatt electric if you do this kind of thing. Now, are there any optimized designs for natural circulation reactors? If you look at many of the SMRs, they are using this integral type design, where all the components of the primary heat transport system is in one vessel, and they totally, the piping is not there at all, and this is what we call the integral type design. And it's natural, if you look at the pressure tube type reactors, they are low natural circulation capability. Vessel type, natural circulation performance is better than pressure tube type. Pool type is still better than the vessel type. And if you go to the integral type, that is the best, so far. And, if you go this kind of things for boiling water reactors and supercritical systems, they don't need the steam generator, and the cost can be much lower. And if you look at SMRs, the cheapest design that people have come across is the boiling water reactor. And the advantage of this design is it eliminates pipes, and it also adapts, the core height is much smaller. Say, it can be as low as 0.5 meter. And, the steam generator also, you have to have less height, then, you will have less LT by D, and then you will have a very large flow rate. And, as of now, people are talking about this kind of reactors. You can have up to 300 megawatt electric. So to conclude, so we have looked at parameters affecting stability in single phase, two phase, and supercritical natural circulation systems. And we found single phase natural circulation systems can be stabilized without affecting the heat transport capability. And you could also have a situation, that if you reduce the LT by D ratio, then you can actually enhance the heat transport capability while stabilizing. So that option is available for both the single phase and two phase, and to some extent the supercritical systems also. Yeah, if you look at so this is just to repeat what we have told. So reducing LT by D ratio increases the stable zone in two-phase natural circulation loops. And we also found type 1 instability disappears at high pressures, although the pressure at which it disappears is found to be different for large diameter loops. And we found type 2 instability can be eliminated in the large diameter loops. And most of the the pressure tube type natural circulation boilers which are used in thermal power plants, they use typically about 2-inch pipe, and in that case, you do not actually observe this type 2 instability. Now, if you look at supercritical systems, a single phase stable natural circulation system can encounter instability while passing through the critical or pseudocritical region where there are steep changes in the density, actually steep reduction in the density. And you find that reducing the LT by D ratio has a mixed effect on supercritical natural circulation instability. And, in some sense, like, it enhances the lower and upper threshold. That is, if you reduce LT by D ratio, we find the lower and upper thresholds are enhanced, and that way it is stabilizing. But instability disappears, and also instability disappears at a lower heater inlet temperature, which is also stabilizing. But then the unstable zone widens. This is happening because, if you increase the diameter, then your flow rate increases. And, then to cross that pseudocritical region enthalpy, so that needs a much larger power. So it is, whereas in a low diameter loop, the flow rate is less. And, that's the reason why that the unstable region is very narrow. And coolant flow rate increase as well as, this increases the lower and upper thresholds, and that way you can actually stabilize. And increasing the pressure is also stabilizing. So that's all. So if there are any questions, I'm ready to answer.
Dr. Vijayan?
Yeah.
Vaidyanathan here. See, there are two things. One is, how do you measure this instability in your experiment? That's the first question. And how do you do such a measurement on an actual plant? Can you just throw some light?
Right. So over here, if you look at, this single phase instability and, and two-phase instability, say either you measure the flow or you measure the delta P. So we were measuring the, flow cannot be directly measured, because our flow can be measured only through delta P, right? So, if your flow is oscillating, your delta P will also oscillate. And say over here, what we are actually measuring is actually the delta P. So the delta P is oscillating like this, and then once it reaches a stable region, then that oscillations die down. And then again, when you reach the type 2 unstable region, it starts again. So either you measure the flow or you measure the delta P.
No, this question comes to me from our 700 megawatt PHWRs.
Yeah.
Is there any measurement on the plant for instability to know really whether it is stable or unstable?
See, in 700 megawatt, they have, like in the 220 megawatt, they have 16 channels which are monitored. The flow is measured, right? They have, in those 16 channels, they have what they call delta P instrument, actually flow instrument. It's a non-intrusive type which they are using. I think
they need to be tuned to, for the frequencies, for which the instability exists. Otherwise, they will not be able to capture.
See, they are also measuring delta T's across the 16 channels. So from the delta T also you can get the instability. See, you will find delta T is inversely proportional to the flow.
Correct.
So therefore, if flow is oscillating, then the delta T will also oscillate. So
again, the temperature measurement has to be suited to the type of oscillation.
Yeah,
it has to response time. I don't know whether the RTD is another response time.
So we did the experiment in our Narora atomic power station, and so we did not find the kind of oscillating type instability, but we had see 1K, 2 channels, the 16 channels are monitored, and we were looking at them. And, when we were doing the experiments at, say, 1% was our proposal, but, we actually did it around 0.9% power.
Okay.
And then we found, we started from, the pump operation and switched off the pump and wanted to see how the natural circulation develops. And then we found, say, there were very different behaviors in the delta P.
Correct.
See, in one, this thing, the delta P, actually went to positive, and then it reversed to negative.
Reverse.
And then again, it came back to positive. Whereas in one channel, it actually went to negative and remained negative throughout the experiment. Now, see, parallel channels have this kind of behavior. See, in any parallel channel. Yeah. So if you reduce the power below a certain value, then it can reverse the flow.
Okay. Thank you.
Yeah.
There are some more questions in the chat box. Professor Munshi, you can also ask directly.
Vijayendra, ye cost of these natural circulation SMRs per megawatt electric would be less compared to the 1000 megawatt?
Not at all. See, not at all. See, if you look at, there are already the Argentinians are constructing a 27 megawatt electric, which is called CAREM. And, it is expected to be commissioned in 2026. And, their cost is, 195 crore per megawatt electric. Whereas our, 220 megawatt, our 700 megawatt, they are talking about, they started with 1200, now it is something around 16 crore per megawatt electric. So the larger the price, larger the power, then the lower the cost per megawatt electric. And in SMR also, there are this 300 megawatt electric boiling water reactors, actually in UK, which is that company which make the aircraft engine?
Rolls-Royce.
Rolls-Royce is developing a 300 megawatt electric natural circulation based one. And that they are claiming that it is 18 megawatt, 18 crore per megawatt electric. So, which is, still higher than our 700 megawatt electric, but it is a 300 megawatt reactor, so 300 megawatt. So if you increase our power rating, then the cost per megawatt comes down. See, the Russians, they have an operating SMR, which is a 40 megawatt, and it is a floating reactor, and it's their cost is 112.5 crore per megawatt electric. And the Chinese also have an operating SMR, which is actually 210 megawatt electric. And it's the university which has made it, the Shanghai Jiao Tong University, and it is operating in their campus. And this 210 megawatt electric, they are quoting a price as 45 crore per megawatt electric. So definitely all these prices are much more than the large commercial power plants. But then, as you said, the total investment is going to be less. When you go to, let's say, 25 megawatt electric, so the total price is going to be less compared to a commercial, large power plant. That is the thing. And, the financing, etc., becomes somewhat easier.
Okay, thanks.
Yeah.
Are there any other questions?
No,
I had one question which has already answered. in response to Vaidyanathan's questions. Professor Vijayan, this is Gantayat here.
Yeah, right. I am
Enjoyed it.
I am seeing your question. Okay. Yeah. Should I see the or you will ask the question and then I will answer?
That has been so now I'm asking a question that the
Lalitji, your voice is going. It's unstable.
There's some signal issues.
I think the instability has creeped in.
No. Okay. Now it will become clearer. Okay, just a minute.
Okay.
Hello.
Can you
hear me
now?
fixed.
Right.
Now it's fixed.
Perfect.
Yeah. So what I was asking is that you had said a pump really gives you one control on the flow, CHF, everything in a forced circulation.
Right.
But what is the equivalent control in a natural circulation while the reactor is on power?
Yeah, see, in natural circulation, till that General Electric 1575 megawatt electric, that reactor, it was actually USNRC has licensed it. I don't think it is, they have plans to construct, but I don't think they have started the construction. Now, the question is, that is 1575 at that time was the largest or highest power. Now, if you talk about single phase, then the driving force is much less. And, the only way you can increase the power rating is, what we were telling, say, if you go to that integral type, integral type, we found, you can have very high flow rate, so we were actually working on one small micro modular reactor. And we found, even for a power of about 15 megawatt thermal, we can get about 900 kg per second flow, which is quite high, so those reactors can go to higher power. That is, their L by D is very less. See, L by D, remember, that is the one which actually increases the frictional pressure drop. So, earlier people used to give that there is something called friction number. If you look at Zuber and Ishii and, all that scaling philosophy, there is something called friction number, which is FL by D. Now, what we have done is we replace that F is equal to P by RE to the power B, and then you get only L by D. So that L by D is the geometric contribution to frictional pressure loss, and the lower the frictional pressure loss, the higher the flow rate. See, like even if you have one...
Is there a flow control valve envisaged?
No flow control.
Like
two-phase, natural circulation system is the power itself changes the flow. Okay. So if you are starting up at a low power, then your flow is very low. Now, as you keep on increasing the power, the flow will automatically increase, and that's the advantage. And see, in thermal power plants, see why they have preferred to use this natural circulation over forced circulation is, see, many times they cannot avoid this, flue gas maldistribution. Flue gas, and then, they found, see, in the channels which are having high
What
power.
happened?
Yeah. So that they have that CHF and oscillatory CHF, and then eventually that pressure tube fails. But they found that if you switch to natural circulation, this problem is avoided, because in case of natural circulation, it will generate the flow which is proportional to the power that is absorbed by each channel. So there is no need of a control that the phenomena itself controls the flow.
Yeah. So the reactor situation is quite different from the other natural circulation in the other plants. Like you given the example of reboiler, where the flow is controlled just by submergence. And similarly, thermal boilers is controlled by the level. So there are some external inputs that are used to control.
Yeah.
But in the integral, you have no such thing.
No. You see, in the BWR, the level is controlled inside the reactor vessel. And even in our ASWR, the steam drum, that is at the highest point, and there the level is controlled. So you have a continuous feed coming and continuous steam going up. So the level has to be controlled. Even in the natural circulation based reactors.
Yes. Great, nice, really listening to you.
Yeah. So
a long time.
It was very nice to see you after a long time. No, I think
are there any more? Sorry, go on. Are there any more questions? Okay. So in the interest of time, we can close here. I really want to thank Professor Vijayan for taking all the way from fundamentals to practical design. This is a very nice talk. I will post the thing. We have a YouTube channel where all these seminars are going to be posted. I'll also circulate it via email and via the DAE WhatsApp group. Thank you, Professor Vijayan. I will get in touch with you one-on-one later.
Thank you. Thank you for giving me this opportunity.
And thank you for, as usual, there are a lot of interesting questions from very knowledgeable audience. So thanks for that too. Thank you. Good night.
Okay. Bye, Vijayan.
So bye. So wish you all a nice evening.
Thank you.